Or is good. High volume control is good. See, I downloaded that thing, right? So it should be. Oh. Where did it download to? Oh, it's right here. All right. Sorry. All right, yeah, let's look at the.
So for B, it says it goes into that the other file where it describes the actual process of doing the backscatter stuff and the fixed window scanning. And then the question actually asks about like the difference between the heavy water, the deuterium oxide, and then the water. Is the answer to that just pretty much what it says before that quote where it says like it swells 15%? Like that was the only thing that I could think about that would but like if it swells, then you're gonna get a lot more information about the water diffusion specifically. Oh, and then if you do it with the heavy
No, it's a contrast issue. So the measurement, he can't see D2O. Like the D2O is invisible. So he only sees hydrogen water.
Okay.
So he takes a polymer membrane. That's the question, right? So he takes the polymer membrane and you can measure the hydrogens in the polymer membrane. So I'm looking at hydrogen. And then because contrast for neutrons, hydrogen's got a big contrast compared to everything else. And deuterium and hydrogen, deuterium's smaller and it's also like negative.
Okay.
So it's like as if you had a
Progress.
negative. So it's kind of weird. So it's index refraction difference squared gives you the contrast. So it's kind of like that's the biggest contrast is H and D, but H is the one that's got the big number.
So it just doesn't catch the D at all.
It doesn't see the, I mean, he's assuming it doesn't see the D.
Okay.
Yeah, so then film, and then you see the swollen film, and they're different.
Yeah.
So you can see what happens when it swells, and then you can put in the normal water in, and you can see the membrane and the normal water, and you can just kind of subtract off the membrane,
Okay.
the swollen membrane.
Okay. Yeah, I wrote a little bit about that, but I didn't reply.
Yeah, so it's basically D2, the way he's talking about it is as if D2O is invisible.
Okay.
It's not really invisible. You know,
Gotcha.
so it's, but he talks about it like it is invisible, and he totally confusion. So it's involved enough that he just does that. So I think that's probably I don't know what he's talking about, but basically I think that D12 would give some contrast,
Okay.
but he just doesn't.
Yeah.
Well, so these things like in IR, if you look at a deuterated group vibration, or you look at a hydrogenous group vibration, so the frequency is like double because the mass is double. It's like you have a pendulum with twice the weight on it.
Of the deuterium.
Yeah. So deuterium's like it's a proton and a neutron, and hydrogen's just a proton.
Right.
So it's got twice the mass. In terms of the yeah, it's got twice the mass. So basically when it vibrates, as if you had a pendulum with twice the mass on it. So the frequency is like half.
Gotcha. Okay.
But so it's a lower tone because it's heavier. So and he's looking at vibrations and rotations. It's the same thing like in the speeds he's looking. So he's looking at certain energy of absorption. So he can say, I guess, in the sense of the quasi-elastic, in the sense of neutron scattering, you'd see both, but the contrast would be different. But in terms of quasi-elastic, since he's looking at a certain energy of the frequency of vibration, then the deuterium one is too slow. It's too low of an energy.
Okay.
It's out of the window, and he's only looking at that window to see hydrogen.
Okay. That's okay.
So it is invisible, I guess, for him.
Yeah.
Although it's kind of weird to think about it. In terms of the structural, it's like weird to look at it that way, but basically for him, I think it's true. It's like you're looking at an IR peak for hydrogen. Then when you put in deuterium, it's somewhere else. It's not there. So you won't see it. Yeah. So it is invisible. Yeah, it's pretty involved, like this thing's pretty involved, so
Yeah.
that's really technique oriented, but he doesn't explain it. It's explained in that other, it's explained in that B book, but you'd have to read the whole first 2 chapters or something, you know, and that's super involved. And that's too involved for what you're doing, you know.
Mm.
Yeah, so essentially the D2O means you can't see it.
Okay.
It's just missing. And then you're just getting the dynamics of the H2O or the H. Yeah. Yeah, I guess if you kind of write down, like have a cheat sheet, like I was looking at a paper on membranes, like the chemical engineering papers, a lot of times they'll just have a cheat sheet at the beginning with all the acronyms you're going to use. And like a chemical engineering dissertation will have there's like the table of contents, figure captions, table captions, and there's like all the acronyms I used, and a list of them. So I think
this is an article. They don't do it.
Yeah, science doesn't do it, like physics, chemistry, they never do that. But engineering, chemical engineering in particular, they almost always put a list of the acronyms at the beginning of the paper.
Yeah.
It's pretty useful. But now, like, you can search, you can say like, where is whatever, you know.
Yeah.
And you can kind of find the first time they use it, they define it. But it would be much easier if he, especially in this case, if he had just defined them all at the front end.
Are the people who are like in other colleges, like Minnesota, like I think we did a whole homework on the people that were from Minnesota, I believe.
Mhm.
Are those people in the physics department or are those people in the chemical engineering department?
You mean for the membrane stuff, or I don't know?
Just for like polymer physics in general.
They're in chemical engineering.
Okay.
Yeah, so that's a kind of, that's the top chemical engineering school in the country.
Right.
But they have like materials, and the materials is all polymers.
Oh, really?
Those are some ceramics too.
Yeah.
It's like ceramics and polymers, so it's all like nanomaterials and polymers and surfactants and stuff. So it's a big department. It's probably like 100 faculty. I don't know. It's huge.
Yeah.
And then I don't know, it's a good place, like cold, I guess. But
Is there just no innovation in like metals? We were still looking at it.
no, there's a guy gave seminar on Friday I went to on metals. So I mean, from my perspective, there's no innovation in metals. You know?
Yeah.
From a metallurgist perspective, we in the department, materials department is like mostly metallurgy now. So they all think that is there any innovation in metals? I mean,
it seems like no from the outside.
Well, it depends where you're sitting, you know.
Yeah.
It's like the guy's the head of materials at Ohio State came to give a talk. And he's talking to Don Lucia about superconductors. And it's like Don Lucia said superconductors ended like in the 1990s, which it did pretty much. It's being used, but basically, you know, the research ended. And they have a guy doing superconductor research, you know. So it's like, but now it's like, I guess he was talking about airplanes. This guy's doing titanium alloys. If you're in the Air Force, or if you're doing like in the Army or something, like there's metals in the Army and Air Force. Because jet engines are made of metal mostly.
Even so, with those, like it seems like we're trying to transition into other like lacquer plastics. Like that's a lot of our company,
Right.
Well, my company does. We just try to transition those from aluminum to a high capacity type plastic, high performance plastic.
What company?
Fremont.
Okay, because all right, if you're a GE aircraft, you know,
Yeah.
it's mostly metallurgy people.
Right.
So
yeah, that's like the vast majority of our stuff is like, at least our aerospace stuff is trying to take the aluminum and convert it into plastics. Like aluminum's and their stuff, it's very easy to bend, and it's really hard to bend it back straight without taking it out and putting it back into a machine.
Yeah.
Whereas like plastics can take a couple hits without that.
Yeah. Yeah, plastics are lighter, I guess.
Yeah.
I mean, there's some trade-offs.
Yeah, I think it's called Vespol. It's called it's like it's poly in that type of thing.
Yeah, I mean, there's trade-offs between the two. Aluminum in particular and titanium are kind of useful, you know, because they're light.
Yeah.
And Yeah, they compete head to head with plastic.
Right.
Like for, say, a can versus a bottle.
Yeah.
You know, so,
Yeah, I was just interested because like usually we hear about like metals, ceramics, and then polymers, but it feels like polymers get like all the love and that type of thing. Like I think when I was looking at materials masters, there was like one class in metals, one class in ceramics, and then the rest were just like plastics and polymers, rubber and things like that.
yeah.
So I mean maybe that's where all the money's at in terms of like innovation, but it was kind of interesting that.
I mean, it bridges easier with biomedical and stuff, but also there's like a lot of metals and like the stents mostly are made of metals and the artificial joints. The contact point is polyethylene, but the thing itself is titanium. You know? So I mean, it depends on your perspective. You know, like which one's more important.
Yeah,
I think there's a little bit more science and in engineering and the interaction and the joint part, the interface.
Yeah.
But I don't know. I mean, it just depends on where you're coming from, I think.
okay.
But anyway, yeah, so he was saying like, well, the next thing is going to be electric turbines for jet engines, for jet airplanes. I mean, they're doing superconductors for that, for the make the electric motors lighter. But I mean, I don't know. I think that probably is going to be like ammonia fuel or something, you know, or something different than it's not going to be like electric. I don't think. I don't know. Maybe it will be. Who
I
knows?
didn't know that was a thing until I took that solar power outage.
Yeah, ammonia is a big deal. Yeah, it's a lot of chemical engineering in the future, you know.
Yeah.
And the technologies to replace things. So, but anyway, it's pretty hard to tell like what's important or not. And like even it could be a superior technology, but it won't make it without the funding, you know, the capital and like politics too are involved. Like who makes the stuff.
Yeah.
So if we have a big chemical
hard for every other university besides Minnesota, because they have 3M there. That kind of like desires them to innovate. Whereas like if you're just doing it in like UC, I mean I guess we do have GE here. But like kind of
we got a lot here. Yeah, there's a lot in Cincinnati, you know,
but
there's more than
random place. Like if you're in Akron, there's probably not a lot of like high level material companies that are like pushing you, I guess, to do that kind of thing.
Yeah, but you had like Youngstown's right around the corner, right? So you had the steel industries centered in Massillon and Canton, and Akron, and Youngstown. And it's all kind of dead. I mean, some of it's still alive, but they didn't do that. Anyway, they have rubber right there, you know, the huge, that's like the #1 rubber city or whatever.
Yeah.
I don't know. It's pretty hard to tell. I think to me, like polymers are more interesting to work in, you know.
Yeah.
But it's interesting to look at. I mean, it's like defects and like stuff and how, you know, so it's a different kind of thing going on.
Yeah, it seems like there's more going on than just, you know, but I mean, I guess in metals, there's probably like, you know, 2 or 3 that are like really leading the way. But for like a lot of these like specialty polymers, like it seems like they're like here to last for like the long run. You know?
There's money to be made in any of the stuff. Yeah. And there's some of it's kind of interesting. It depends somehow, like you fall into a thing and you just kind of keep doing it.
Yeah.
So it's really hard to tell. In the end, like though, if you go back, it's all based on the same stuff. You know, so there is like a connecting point at the root of the stuff. And the connecting point at the root is really a lot of it is metallurgy based. Like it isn't, so polymer is more like do science down the road, you know. So you have to keep in mind that not take it that seriously because it's kind of like it isn't metallurgy you can take seriously, you know. I mean, whatever, uranium enrichment or whatever, you know. So yeah, I mean, or whatever they're doing, it's kind of serious, I guess. But polymer is a little bit more flexible, like in many, you know, fun type thing. But so I wouldn't say there's nothing going on in metals, you know.
Sure. Yeah.
I mean, it kind of starts to look that way, but basically, the metals has a huge political base, you know.
Yes.
And the funding agencies, and then the military. Aerospace and space stuff and things. So it's not going to go away, you know. I mean, and I think there's fewer people going into it too. So in that sense, it's less competition. And it's not actually not as challenging as polymers right now, and not as
I agree
nowhere
with that.
near as competitive, So in that sense, it might be a good area to go into,
Yeah.
It's like right now is a really great time to go study nuclear power, even though it's dying.
Yeah.
Because they're dying, desperate for people to work in that field. Everyone is looking to hire people. I mean, it's gonna last one more career, it's like, that's all you need to worry about is that the next step for you. But I mean, I think eventually nuclear power is gonna be like so far gone, it's too expensive for one thing. I mean,
Yeah, it kind of seemed like a pipe dream to be like trying to get out.
fusion energy, I mean, that's insane. They've been working on that forever.
Yeah.
And anyway, who knows? If they, when they see success, then I'll say, yeah, it's a good idea. But I mean, it's so far, but the original like uranium-based stuff, it's kooky. But there are a huge number of jobs in it. It's like probably it's all pretty well defined. It's gonna be pretty easy,
Yeah.
So I mean, you can make the reactors. Anyway, it's pretty interesting. Like you were in that solar Africa class, or no, in thermo class. I used to teach thermal, but they took me out of it because it was too hard, or something. I think that's my impression. So anyway, we did nuclear power, and like if you look at how the design of those a high pressure reactor. So the U.S. only uses high pressure reactors because the Navy needed high pressure reactors to have like a confined area where you didn't have the heat exchange fluid get radioactive.
Okay.
And also the high pressure reactors are smaller, so they fit on an aircraft carrier and a submarine. So there's a lot of nuclear engineers trained in high pressure reactors. So all the commercial reactors in the US are high pressure. And the pressure is like huge,
Yeah.
So the cooling fluid is something like 100 atmospheres or 200 atmospheres or something. It's moving like at almost sonic velocity through the core because it has to cool it so fast,
Yeah.
So the whole thing is highly radioactive. It's insane. Like if you look at the design of a high pressure reactor, a commercial power reactor, you'd think that these people are nuts, like to do that. It's so dangerous,
Wow.
Every one of our reactors is that design.
Yeah.
And then in countries that we influenced that design, like Japan has that design, but everyone else is using this low pressure reactors, everyone is like sane. So I mean, it's pretty weird, like kind of you see. Anyway, it was all just because we had that technology and we had it developed so well for them. Navy's never had an accident.
Yeah.
And they have a lot of reactors,
Okay.
So I mean, it would make sense to just let the Navy take over all the reactors, just like let them run them and not make it commercial.
I think there's like a lot that are like defunct now, right? There's like a lot that are just, like, the companies that pulled out or whatever, or they shut down.
Yeah, it isn't competitive.
Yeah.
Like the one in Ohio, the state is subsidizing them to keep it running,
Yeah.
So it's like basically it's not competitive against solar. Solar is the
Right.
cheapest energy right now.
Yeah.
So solar and wind, so basically the nuclear and coal, and then after solar and wind is gas, gas turbines.
Yeah.
And there's plenty, we got so much gas with the fracking, right?
Right.
So basically, and gas is less carbon footprint kind of, except at the source. There's a lot of leakage at the source,
Yeah.
and that stuff, the methane, I think it's like 14 times CO2 as far as energy capture, whatever in the atmosphere. But the lifetime of CO2 is like 100 years, and the lifetime of methane is like 10 years or something.
Yeah.
So it's kind of like, it's 14. So in the short term, it's a disaster. But in the long term, it's not that significant.
Yeah.
And maybe it's the same as CO2. So it's kind of how you want to look at it, like the immediate melting of the glaciers or like long-term death of all life on Earth. It's like methane's probably an even trade-off,
Yeah.
I guess, But anyway, yeah, I don't know. Anyway, it's kind of hard to tell what field to go into. I think Polymers is interesting, in terms of companies, like it's great, in terms of academic research, I'm kind of wondering like how far it's going to reach, because it's been going since the 60s,
Right. Yeah.
and it's everything reaches a peak and then falls down. So you have to kind of watch that curve where you're sitting on it.
I mean, the general plastics of our course are like very commoditized. But even now, when we see a lot of these companies that kind of had like a very tight squeeze on their industry, like even us, like we have Kevlar and Chemours now has Teflon. That stuff's kind of becoming commoditized
Mhm.
because other companies can make it, or then maybe they can make it cheaper, or you have alternatives
Yeah,
as well.
yeah.
So, that kind of squeezes it where it's like, okay, well, this thing now become a commodity. There's not growth in a lot of that stuff,
Mhm.
unless people magically start using Teflon for everything.
Yeah.
Like we know how much we're gonna sell in 5 years, that type of thing. Like
Mhm.
that makes it hard in that kind of that type of thing. But people are using more like laminates. Laminates, I feel like have really blown up in the last couple of
Uh-huh.
years. And people are trying to do like substrate things for metals and what as well, like
Mhm.
trying to put like Teflon on top of copper and things like that. Like that's kind of like they're innovating it in a different way. They're no longer
Yeah.
like trying to optimize chemicals. They're just trying to optimize it like mechanically.
Yeah.
It's very like strange the transition between.
Yeah, this big transition going on.
Yeah.
Yeah, it's no longer like so much new chemistry coming in and more like just how to use it.
Yeah.
Except for some niche markets, like niche areas where a couple grams is worth something.
Because
No,
well, it
but-
seems like the 50s, 60s, and 70s, like they would just like mix two things together and it'd be a new like polymer.
Yeah.
And like, all right, well, this is
Yeah,
this is it. This is $1 billion.
yeah, it was a boom time. Everything was developed. Yeah, it's true.
Yeah.
So in that sense, that was kind of a exciting time, I guess, to be in polymers.
Yeah.
You didn't know exactly what was going to come along. Even like when I first started, it was like metallocene polyolefins, and they won a Nobel Prize in the metathesis polymerization stuff. And then like that was kind of like going to replace all like PDMS basically, any kind of rubber.
Yeah.
So it didn't replace it.
Maybe that's
basically-
just how every industry is though, because like even in like the wood fiber composite type things,
Uh-huh.
even now they're not like they know all the materials, like they understand all of it, but now they're kind of into like they're doing more like how to optimize insulation and things of that nature.
Mhm.
Instead, and that's more like a materials like a post chemical process. Now they're
Mhm.
trying to optimize that.
Yeah,
Like the chemistry is already there; they're not replacing any of that.
yeah.
It's just the actual like application of it that they're fixing.
Mhm.
So it's very weird. I don't know what to do with that as like a chemical engineer,
I mean, chemical engineer is going to do fine, like you'll do fine as long as you can keep flexible enough and broad scope enough,
Yeah.
Like I had a guy for a PhD student that's working at Lyondell. He was from Alabama, University of Alabama, BS, chemical engineering. Went to work at a pulp company, paper.
Yeah.
And then switched from chemical engineering and switched, like just walked into polyethylene. And then it's like they use polyethylene to coat paper. It's
Yeah.
used in the process,
That's fair.
I mean, so you can make an argument like,
Yeah.
and then the guy, and another guy went from Lyondell to International Paper, and he was like a group leader there, and he went to International Paper in Seattle, kind of along those same arguments like coating and protection, And then another guy from Lyondell went to Cabot in Chicago, doing polishing of wafers,
Yeah.
chemical, mechanical, CMP.
Yeah. We do a lot of that.
I mean, that's got nothing to do with polyethylene, nothing at all. I mean, maybe they put some silica to keep the films from sticking together. That's it, That's the only place there was any connection at all. So if you're an engineer like that, you got to keep your breath, of what you're doing. Maybe go to the ASCG meeting or something, or whatever processing meeting, packaging, and then
That's fair.
yeah. So you got to be able to be flexible.
Yeah. That's
And
what
keep
I
kind
tell
of
them.
running with it,
When I TA for the freshman students, that's what I tell them too. They're like, hey,
Yeah.
your co-ops could be in completely different stuff.
Mhm.
And then if you're in laminates, you can transition that into metals because like a lot of that stuff is, it's the
Mhm.
same type of machines. It might be bigger
Yeah.
for metals, but it's the same machines
Yeah.
and same technology. So you'll be able to kind of leverage that to a different industry.
Yeah, and the companies, and especially with it going commodity, it's cyclic,
Yeah.
So like Lyondell will hire like right now they're hiring a bunch of people. I mean, they're just hiring anybody.
Yeah.
Then then the market, then they build a bunch of plants,
Yeah.
Then we oversupplied, like as if they couldn't see a sine wave, I mean, then it's like, oh, we gotta fire everyone. So they
Yeah.
fire everyone, boom. And then they realize they don't have enough people to do the thing when it comes back up, you know? So it's just a cyclic thing, and you gotta be able to jump industries in those
Yeah.
times, you know? It's a little nerve-wracking. I mean, it's good to figure out how to not take it too seriously if you're going along that road, because otherwise you shoot yourself, you know, when the pit comes, and save up some money while the cash flows in.
Yeah.
It's like this boom bust in California now. Like my daughter was working at Beyond Meat, and they were hiring people in LA, like phew, so much money, and all those other like Tesla and all these companies. The pay was huge, you know.
And then, like, I think COVID happened, and they were like, yeah, we have no idea what's about, so right after that.
Oh, that's a great place. It's right on the beach.
Yeah.
I mean, it's on
I
the
look
beach,
forward
you
to
know,
it.
it's so nice. Like, it's such a nice place, and the pay was great, you know.
Yeah.
What are the future gonna be like with those kind of companies?
I mean, the future is fine. It's just like the short term. It's basically when the interest rates went up, and then the investment in venture capital dropped, and these companies are living on like, oh, that looks like a growth. That's a great idea. You know, I'll give them like $10,000. It's going to double next year. You know, no problem. But when the interest rate drops or goes up, then their competitive advantage disappears. And they didn't really have any future to begin with, you know. I mean, they had a future, but basically, long term, there's a future. People are going to stop eating cows, and they're going to start eating peas or whatever, you know, because basically the earth can't hold that many cows.
Yeah.
I hate to break it to you, you know. I know Nigeria lives on beef, but basically no one's going to be eating beef in 20 years.
Yeah.
They'll think it's like gross, you know, because like, why would you eat a side of an animal when you don't have to? But, and it's better for you too. Like everyone's dying of heart disease.
Yeah.
So it's basically, you don't need it, you know, but
So it's gonna be a shit.
yeah, it'll be a shift, and these companies are going to be in on it, or maybe it'll be Kellogg or someone that buys them out, you know. But basically, they'll make money in the long term, but in the short term, it's all this game. The stock market has nothing to do with logic. Like engineers shouldn't be involved in the stock market. I'm absolutely convinced of that after wasting money in it. Because you see like,
Transition.
yeah, well, if you're doing, derivatives of some crazy, whatever, Monte Carlo, or there's something they were doing, all the simulation stuff we do, they do there, you know, put it that way. So, but anyway, yeah, they can convince, that's a one plan too, like they convince someone else that because of this math, they can predict the future.
Yeah.
Well, that isn't exactly how it works, you know, because the future is just based on some Joe Schmo guy, billionaire or whatever, decides to like go buy Facebook.
Yeah.
That's the future. And like, if you had thought about that, you could have put your money in the right place to make a ton of money off that. But, you know, you can predict that with a computer.
Yeah.
You know, it's some insane person doing some crazy thing. It's like, you know, maybe if you're a psychologist, you should invest, you know, otherwise CDs are pretty good. That's why I see it now. But, anyway, not sure where that's going, but anyway, yeah, they're doing, anyway, they were doing great for a while, and then everyone just, they fired everyone, you know.
Yeah.
But luckily she went to law school the day before they fired everyone. So it's like, yeah, so she should do okay, I guess. But yeah, a lot of people she worked with don't, you know, they've lost their jobs there. Yeah.
In terms of innovation, I guess this would be the last question for you, actually. A lot of the innovation, I guess, in my mind, comes from like these massive companies.
Mhm.
Is that like actually true, or is a lot of them influenced by like professors that are doing research?
I mean, I have a friend at P&G. He's retiring this year, but he started out doing research, PhDs, biopolymers, which they bought from ICI, which ICI bought from someone else. Okay,
They're all over now.
anyway, so not PCB, I mean PHB, polyhydroxybutyrate, is that what I said? Or anyway, so it's biopolyester. You can make it with soybean plants. So Procter & Gamble bought a bunch of soybean land in Kansas, like a huge amount. Like the future is going to be growing plastic in Kansas. And then they transgenically modified the plants. And then they had a pretty big staff. They had a staff of like 20 people working on this project in wherever the central research place. I don't know of it now. But anyway, so they closed that place, you know, they closed the research place, one day the CEO said, like, why are we throwing all this money away in this stuff? They had made diapers like biodegradable. The entire thing was made out of PHP and
Wow.
PHP copolymers.
Yeah.
I mean, they can do it, they just did it. They had the products ready to go in case like
Yeah.
there was some kind of environmental revolution. And then they said, like, we have to go this way. They had the equipment, everything set up to do it,
Yeah.
It was just cheaper to do it with polyethylene and polypropylene. So anyway, one day the CEO said, oh, look at all that money we're paying on this stuff. Why are we doing that? Let's lop it off. So the stock price went up. Stock price is great for P&G. That's a good investment in the long term, I think. But anyway, the stock price went up. They fired all these people. A Japanese company came in and bought the people and the patents. They bought the entire operation. They didn't move it to Japan. I don't know. They moved it to North Carolina or somewhere. And they had like guys that were like had won the science award and stuff like Asao Noda. In fact, the stuff's called Notoprene. Or Noda something, Nodex something. That's what PHP is called now. So the guy he'd done some stuff with it, he didn't invent it.
Yeah.
I mean, it was invented by the Canadians or something, or the British or somebody. Anyway, the Japanese company decided to transgenically put it into yeast. So they just brew beer and make plastic,
Yeah.
or bacteria or something. So it's just a fermentation process.
Yeah.
And that's how they're making all of it now. There's no soybean. I guess probably the soybean land in Kansas, the price dropped, or something.
Yeah.
So that would have been a good investment to like buy it before P&G came in and then sell it before the whatever. So anyway, so that's how industrial research works in the US. Like a year and a half after that, the science director at P&G said, oh, look at all this bioplastic. Why aren't we in that?
Yeah.
And then they started a research effort in bioplastics. Well, they hired like 5 people. That's how industrial research works. It's a bunch of crazy people running around in circles, all right, the stock price, meanwhile, took a big jump when they sold it off and took a big jump, like a small jump when they decided to go into it.
Yeah.
So the people doing the stock market don't even know what plastic is.
Yeah.
They're investing in it because, oh, they have some new ideas.
That has to happen.
And then, oh, they know how to fire people. Well, that's great. It's like, this is how the stock market works,
Yeah.
So capitalism is not going to answer our problems.
That's going to happen often because there's at 3M, there was a lady who made gap fillers for electronics in the 80s. And she went to her boss and was like, hey, I just discovered this thing. The 3M said, no, we don't want it. And you can have it. And she put it in her name. She left, started her own company. And we just bought that company for like $2 billion.
Yeah, like Gore-Tex is the same thing. That was a DuPont.
Oh, yeah.
Gore was a DuPont researcher. They said like, this is going nowhere. He went just across the street, I think, and set up a factory making the sportswear stuff and everything.
Yeah.
It's like Gore's doing pretty good now. It's not the same as Al Gore's, another Gore, but
It's W.O. Gore.
Yeah. That's a good company to work for, apparently. Yeah, because they have, so they don't, you go in and you just float, right? They train you or something, then you float, and then you get picked up by teams that are attacking, like kind of 3M does that too on a bigger scale. But basically, there's teams of like 10 people, and they'll go after some product line, and that they'll recruit like a basketball team. Like they'll look to see who they want to join the thing. Yeah, so it's like, and it's supposed to be a really exciting place to work. Like people really like working there. So really high satisfaction level. It's kind of a really different business model.
Yeah.
But apparently that's a good place to work. I mean, of course, if you're the guy that never got picked for the basketball team, it's not going to be good. So they weed out the people that aren't doing stuff that way. Yeah, I guess, but it sounded like there was no crash and burn thing. Like basically they had a home for everybody, but you wouldn't be on the A team, whatever. So, which is how it would end up anyway. But so, yeah, there's different ways to do it. I mean, 3M has that kind of decentralized effort too, which it's not good for research, it's all business. I mean, maybe they copied 3M or something, because we probably used to have this huge research center.
Well, we still do, but we don't, it's not part of our manufacturing. Like we don't even communicate with them really. So we do put a lot of money towards our experimental station still.
Yeah.
But even so, it's a lot of it's very separated from everything else. it's kind of hard.
That was like the last great place to work,
Yeah.
because it was just like a lot of really bright people and like
And there
product.
still is there's very smart people there. It's just
Oh.
it's very hard when we don't communicate with
Uh-huh.
each other. That kind of makes it pretty difficult.
It was kind of like Bell Labs there and the IBM in California.
Yeah.
And then like IBM and Bell Labs disappeared kind of, and then like that was the last one standing.
Yeah.
There's more
Have you seen
chemicals.
these massive, like 800 company places in like Richmond, Virginia, something like that. Maybe it's North Carolina, where it's like there's like 800 companies in a span of like, I don't know, 25 miles.
Huh.
Just like there's tons of companies in the same place.
I
It's all
see.
just companies.
I haven't been down there. I haven't been to that area at all.
Yeah, there's just a few of them in America, and it's like
Uh-huh.
the 800 companies just like
Yeah.
off there, and all these other like
Yeah.
companies. It's strange, it's weird.
I mean, Cincinnati's pretty good though. If you look, you have to look because you don't see anything like like I didn't see until I taught thermo, and then people flunked. So I said we do tours.
Yeah,
Like you could replace your quiz with a tour.
Yeah.
So we did tours every week, and then like we went to every chemical plant in Cincinnati.
oh, really?
But actually, we didn't scratch the surface. Maybe we went to 10%. Like there's so much industry in Cincinnati. It's unbelievable.
Boys here, there's a lot.
They're just like hidden in little corners. Like you drive by to go to the store, you never notice there's a chemical plant there,
Yeah,
And then you go into it and it's like, wow. And it's like really specialized chemical. It seems to be really important, It's like being made just on the street in the back street somewhere,
Yeah.
I guess it must be that, I don't know why it's located here like that, but basically, anyway, a lot of it's supplying P&G.
yeah,
Like a lot of it is like materials for different soaps and things and that kind of
Yeah.
stuff, but
and then probably just spin offs of different companies and then mergers, and they just take it. Probably.
yeah, I guess, I don't know, like they have the big animal fat thing, and then the other animal plant fat thing, BASF went next door to it. It kind of made sense, I guess.
Yeah.
And then like, so like, yeah, there's a lot of stuff though. I mean, it's just like everything.
Because when we did Delaware, where DuPont started, there's like 6 or 7 companies that are still headquartered there,
Hmm.
but like they just spin off. So like it's companies that you would probably recognize, but you would like, yeah, why are they at a random place in there? And it's like that's why. It's because they started at DuPont. They spin
Oh,
off.
yeah,
now
DuPont
they're
spun
on
off a
Delaware.
lot, but the tax is good in DuPont, in Delaware too.
And direction.
It's like everybody has a headquarter there. They have at least a PO box,
Yeah, yeah,
So
at least the PO box,
Yeah,
yeah,
it's like a tax thing, but
yeah.
yeah, that's an interesting state. But that University of Delaware was one of the first schools in the United States,
Oh, really?
Yeah, it's older than most of the Ivy League schools.
Oh, wow.
It's pretty weird. Yeah, all right, so, but they had like Penn tried to crush them when they formed,
Yeah.
Penn was older, like slightly older, like 5 years older than University of Delaware.
Oh, really?
So they tried to keep them from form, like there was a competition, because we were kind of close, I guess. They weren't even that close, but basically Penn hindered them from growing, as much. So they kind of had this thing going on. But a lot of the early Polymer research was there too, like a lot of it, and still now,
DuPont has a lab there.
Yeah, there's a big microscope lab that DuPont paid part for.
Yeah.
But I think they have a whole building just for microscopy.
Wow.
But yeah, so it's a microscope center. And they have a scattering center too, like the national center for that. Although I don't know, they don't really have much expertise in that area, but somehow they got this center. They're good at, anyway, they're in a good location. That's the thing, like right in the middle of the Eastern Corridor.
Yeah.
And they're right on 95. So it's like,
Right.
it's kind of like easy on, easy off. So, but anyway. All right. So, so anyway, this stuff. All right. So I wanted to, they got like 175 slides. It's daunting. Anyway, I already kind of went through this. These are like some of the top candidates for membranes, right? So you have the cellulose nitrate, cellulose ether. So cellulose would just have hydroxyl groups on the side. I was reading about ionic liquids. So ionic liquids is what the electrolyte is in a lithium ion battery, this phosphate thing, fluorophosphate, which is deadly. Like that'll turn into HF. Air hits it, boom, and then when everybody dies, it's in your cell phone. And then that and some nitrile thing, like aromatic nitrile, makes an ionic fluid that's the electrolyte that they use, right? So anyway, that'll dissolve cellulose, this stuff. Otherwise, nothing else dissolves it because it's polar. So you have to put these side groups on that make it dissolve in water, basically, or hydrophilic, and then we'll go into like other kinds of solvents. So anyway, that's cellulose is cheap. You know, it's all around us is cheap. So if you can modify it, it becomes like kind of the first thing you'd use for anything. And then acrylonitrile is one that's used because it's got a low solubility in water, and then it's got a solubility in some organic solvents. You know, so basically you want to have something where you put it into water and it comes out right away. So then you can get this rapid, kinetically driven phase separation, get some kind of microstructure forming up. And it's slightly controlled. And the sulfones, so it's this S with two O's on it, two carbonyl groups on it. I guess that's not a carbonyl, it's probably a sulfonyl group. And so anyway, and then this fluorinated polymers that are used for membranes too. And then there's some specialty things like these aromatic polymers that have higher strength, you know, so higher strength and thermal stability type polymers, right? So anyway, so there's a lot of categorizations of things. So if you're doing gas separation, it's called a dense membrane. It's got no pores in it except molecular scale pores, right? So, and this is going to do something like separating ethane from ethylene. So you get, so that you do cryogenic separation for the gases from the oil well. So you know, you cool it down, you can make a liquid, and then by the different temperatures, you can take off the different cuts. But the cuts for ethylene and ethanol, you can't do it that way that well. It's really difficult to separate. So like membrane separation is a way to go because there's a size difference between the two molecules. So you can kind of look at the free volume of the polymers and then somehow get the polymer to absorb into the, or to solvate into the polymer and then transport across it. And if the rate's different for those two processes, and you can separate the gases, right? So you end up with, this is the transport membrane flux. You have the pressure, so you have the gas on one side, pressurize it, and the area of the membrane, so you can figure out ways to make the area larger, like just have a huge membrane that's rolled up, and then you get the area that way, right? So the pressure is a problem. Like if you don't have a strong polymer, it rips. So the way to get around that is have a small, so pressure is forced by area. So if you can have a small area, then you can get a lower force. That means the polymer won't rip. So you want to have like a small area, but a big area at the same time. So you can do that by putting the membrane into a tube and then have a really small diameter tube. So if you're working with high pressure equipment, you usually have tiny tubes because it's going to be harder for them to blow apart because there's less force on it. The smaller the tubes, the safer the thing is. Right, so HPLC, it's all little teeny tubes, like 1/8 of an inch diameter tubes are smaller, right? So anyway, so the same thing here. You want to have small tubes so you get less force on the fiber membranes that you're doing. Then you want to have a lot of them to get the area up so you can get the flux out of the thing. So you want bundles of thin fibers. That's kind of how you solve this problem, right? And then delta P is the differential pressure, P is a permeability. It's like the transport. So then the permeability of whatever it is, so it's going to differ with whatever it is. Like if it's ethylene or ethane, then you're going to have like a separation selectivity. If you, so either one, the other one's going to be enriched in the feed stream. So basically, you're not going to do it with one membrane. You're going to run it through multiple times and then get the concentrations to where you want them to be. Right? So anyway, this stuff's from the 1960s, I guess. This kind of idea, picture of what's going on with this. And these kind of gas separation membranes are like the parent membranes, right? So there's a lot of different kinds of membranes. So you want the thick, in order to boost the flux, you want a smaller, L's the thickness. You want as thin as you can possibly get it, but you can get to like 20 like less than a micron now, like 100 nanometer thick film using this like either the interfacial polymerization or some kind of coating process. Right, so you can get really thin films, get a higher flux, but then those films are going to have like they're going to have defects in them, like this, right? So you have this really thin film, 100 nanometer thick film on a porous substrate somehow, either separately made or made at the. So you can either make the substrate in a separate process and then drop this onto it, or bring the substrate up to pick it up, or you can make this all out of one material, right? But then these defects are a problem when you get to 100 nanometer film. So the way to get around that is this Heinz tripodi thing. So you put PDMS, polydimethylsiloxane, on the surface. It doesn't show it here, but if it can fill this pore with the PDMS, then the transport of the material through that pore, because it's thicker, so this goes as 1/L, you can cut the flux through the pore enough that it only goes through, in other words, it's going to go through this rather than that. Right. So if you can fill in those holes with something that's got a lower transport than the membrane, then you can win this game by coating it and then covering up the holes that are going to be there. If you have 100 nanometer or less film, you know, then there's definitely going to be defects in it. And you need to put these sealing layers on top to pack it. And then there's like a packaging process going on here. Right, so this is an industrial scale. Like this, people do this, right? So anyways, that's the kind of game. That's the game with that kind of membrane. That's a non-porous dense membrane. So like I said, like these are just some of the other kinds, right? This is this solvent, non-solvent phase separation membrane, where you put it, you have your polymer in a complex mixture of solvents, and then and some non-solvent sometimes, and then you drop it into water. It's always water as a non-solvent. And then it'll precipitate out, and there's a gradient in the process. And at the surface, you get a thin separation layer. You can make the whole thing in one pop, right? And then, so you can also take this kind of membrane and do a Langmuir-Blodgett film, and then deposit it onto like a polysulfane substrate that's porous. Or you can just make porous membranes for different kinds of separation and change the pore size. And then there's these other kinds like sulfonated polystyrene or fluorinated, so you can have anion or cation transport membranes for like dialysis, or salt, removing salt from water, electrochemical salt removal. So basically, you'd stack up anion conducting and cation conducting, boom, 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 and put opposite charges on the two. Then the in-between channels would be like brine, and then other channels would be pure water. So it's pulling off the anions one way, the cations the other way. And you're doing that in sequence of a bunch of them in a stack, right? And then you connect the right tubes to the right place, and you get pure water and brine out of it, right? So, right, there's a lot of this electrical charged membrane. Also for fuel cells, like you're going to have something like this for proton conduction in a fuel cell. And then there's like these liquid filled pore things. So you make a porous material like the polysulfone, and they fill the pores with a fluid that's going to be your separation. So this could be a lot of things. So this can be used for enrichment of nuclear fuel. It can be used for separating proteins and stuff, different kinds of biomolecules. So you put in a coupling, something that couples to the protein in this fluid, and then it can transport across the membrane. As long as the pores are small enough, then the capillary force keeps a liquid trapped in there, and that can be an active transport layer, right? So this is kind of a newer area, I guess, as far as I can see. This is kind of relatively newer. This is pretty old. So this it's like the 1950s on the left and the 2000s on the right. That's just kind of the way this is going. I mean, these are a little bit higher tech, I guess. Also less used, right? So this is the bulk of the industrial, and this is like the stuff that's more specialized, like if you need to purify a bio thing for drugs, you can use that kind of technique. So this is a map that shows so say you're doing salt, removing salt from salt water. And this is a thing that's kind of hard to understand, this x-axis, but basically pressure goes up. So if the pressure differential goes up, then you get to reverse osmosis, or you're driving the fluid through the membrane. And the pressure goes down, and you get to filtration, like this kind of ultrafiltration thing. Microfiltration, ultrafiltration, and finally you get to osmosis. Like the pore size is changing here too. And then the molecular weight that you can separate, as you get to higher things, you're going to basically in the end, you're going to separate like sand from water or something, like big micron sized 100 micron things. And then as you go down, I'm not sure what the units are here. 10 nanometers, I think, is what this is. But so anyway, so finally you get to 10 nanometers, maybe 1 nanometer. That's kind of the best you can do for osmosis, like removal. So that'd be like salt, NaCl would be like over here. Anyway, it's just a map of, you can define the different regions, right? Nanofiltration, ultrafiltration. And then this is supposed to be a schematic of the size of the things you can separate with the pore diameter, but it's not a very good job of it. Because if this is 2 angstrom and this is 1,000 angstrom, that's like 1/10 of this, not 1,000th of that. So like the size scale, relative size scale isn't very good here, but this is the kind of mapping of the different types of membranes that you can look at. Porous dense. All right, so we talked about that already anyway. And this stuff, this is just showing how, if you're talking about the two judgments of a gas separation membrane, it'll be selectivity and the flux. Right, so you can see, you can get things, so the selectivity you want to be large, maybe 100 would be good. And the flux you want to be large also, but you can't, when you get high flux, you get low selectivity. So there's a trade-off between the two things. Right, so so basically the answer to that is to go to the highest selectivity, like the acrylonitrile, and then make it super thin so you can boost the flux up, right? Because you can make this number to be nanometer scale, and then all of a sudden your flux could be high enough, like 1,000 times higher would bring you up into the silicon rubber transport area, right? So you can play around with that pretty easily if you have a strong polymer. So in the end, you want a strong polymer with a good selectivity that you can process into really thin films. And then you can start to use this equation to your advantage to do a separation, right? Gas separation, say. Then the economics becomes like, is it cheaper to cryogenically separate it? Or there's like 4 ways to separate things. Can't remember them all, but basically membranes is going to be one, and it's going to end up being a decision based on how much it costs, right? In other words, pressure is going to cost something, especially if you're talking about like 60 megapascal or something. A pump to do that, like 600 atmosphere, is like $100,000, just a small scale one. So if the pressure gets to be so enormous, and then also you need the strength of the membrane. So if the pressure gets too enormous, you can't drive the flux just with pressure. You need some pressure, but you can't do that. Like the thing will fail. Also, the pumps cost too much. So anyway, you have to somehow balance these things out, and the way to do it is with the thickness. So everything's going to be like to make as thin as possible. This thing, the resistance model, is that thing I mentioned. Like you put the coating on. If the coating fills the holes, then you can get less transport through the hole than through the membrane. Then that solves the problem of defects when you get to such thin membranes. And let's see. All right, so this is also gas separation membranes, just showing the transport issues, and then versus the so this is mapped. So the two things in this equation are the permeability. Permeability is made up of solubility let's see, permeability is made up of solubility and diffusion coefficient. I have that somewhere here. Anyway, P is solubility times diffusion coefficient. It's definitely written here someplace, but anyway, so this is a map of diffusion coefficient and solubility. So basically, you want to be up here to get a good permeability for the membranes. So you can see, like, and for different gases, that's a different number. That's good because you want to separate like nitrogen and oxygen, for instance, when you want to make oxygen for medical use and nitrogen for whatever blanket, right? So basically you can do that with a pressure swing absorption with zeolites, or you could do it with kind of cryodistillation, or you can do it with membranes. Like there's all these different problems. So the pressure swing absorption with zeolites, so at high pressure, the polar one goes to the surface, and then you can separate the non-polar one, and at low pressure, you release so you go through a cycle, right? So that doesn't involve membranes. That's just a zeolite, right? A solid state. Or you can do it with a membrane, with selective membrane. So you have to figure out like which one's going to cost more between those. Then you can do it with cryogenic. You can separate. This is a big problem. Like air is nitrogen and oxygen, and you need nitrogen, you need oxygen. It's like it's all around, it's free, but basically you need a process, right? So anyway, so why don't we quit there, and then we got enough to do Wednesday easily here. So it will probably be membranes paper this week too, which will make you happy. Probably be more of an industrial paper, like instead of the neutron scattering thing. Yep. All right. So
Okay.
yeah, thanks.